Hello, everyone. This is the fourth webinar in the Powermax series. Our first two webinars introduced Powermax Industrial Solutions, and the third webinar provided details of Powermax Commercial that offers industry-leading microgrid control solutions. If you are unable to attend, the recording is available at SEL website. Today, we will be diving into Powermax utilities or remedial action schemes. Our agenda today includes introduction to the Powermax system. We will then focus more on Powermax utilities, where we will address power system design and engineering challenges, discuss the remedial action scheme's objectives and strategies. We will also present a couple of case studies. Finally, we will take a look at how we perform system validation and testing for such systems. So what is Powermax? SEL Powermax is a scalable, integrated power management and control system composed of relays, control hardware, and software, all designed by the experts in the field of power system. The objectives of the Powermax control system is to provide energy assurance, maintain system stability, provide safe, efficient, and reliable operation for the utilities. Powermax solution has a number of different applications focused on different industries and customer requirements. Powermax Industrial and Commercial were covered in earlier webinars. Today, our focus is Powermax Utilities. This application is more focused towards wide area controls and remedial action schemes. Powermax Utilities solution offer visualization using HMI SCADA packages along with event reporting and sequence of events. It offers remedial action schemes that coordinate with existing protection schemes or protection philosophies and relay settings. This solution also includes load and generation management that can include priority-based load shedding, generation shedding or runback, as well as HVDC runback. The solution is geared towards providing system stability for wide area and protect assets such as transmission lines from overload conditions. Powermax Utilities solutions can comply with regulatory requirements such as NERC PRC 012-2 and NERC PRC 05-6. In this day and age, all power control systems need to have network security component. Powermax utility solutions are developed with cybersecurity in mind from the ground up. Let's take a look at what does remedial action schemes mean. NERC defines it as a scheme designed to detect predetermined system conditions and automatically take corrective actions that include but not limited to adjust or tripping generation, loads, or reconfiguring a system. These systems maintain BES stability, voltage, and power flows, and limit the impact of cascading or extreme events. NERC definition does not include systems such as decentralized under-frequency system as remedial action schemes. However, internationally, such solutions can be part of remedial action schemes. In today's presentation, we will discuss solutions that are identified as remedial action scheme in both North America and other parts of the world. The RAS scheme have been called with different names before, such as SIPs, System Integrity Protection Schemes, or EECS, Electrical Emergency Control System. The NERC PRC 012-2 purpose is to ensure that remedial action schemes do not introduce unintentional or unacceptable reliability risk to bulk electrical system or BES. As per the standard, RAS can be further identified as limited impact or other RAS. The limited impact RAS are defined as such that the inadvertent operation of the RAS or failure to operate does not cause or contribute to bulk electrical system cascading, instability, or voltage collapse, or unacceptably damped oscillations. My colleagues will later discuss what are the different redundancy options available and how these systems can be tested. Now that we have defined what a RAS is, let's look into objectives and challenges associated with the remedial action schemes. The main objective that RAS fulfills is to prevent wide area outage, to keep systems stable even when disturbances occur. The RAS system takes corrective actions after an event such as loss of transmission line or generation that can lead to BES instability. It limits the impact of cascading or extreme events from propagating. Mr. Ashish Opreti is going to touch on its stability classifications and corrective methods later on. RAS solutions can be utilized to operate transmission corridors at a higher capacity and increase the reliability. In some cases, over 50% more power can be transmitted across existing transmission lines. This frees up capital expenditure instead of building new transmission lines. Distributed computing and communications create smart transmission grid management for adding renewables and distributed energy resources. When designing a RAS system, there are design considerations that needs to be taken into account. The design challenges can range from identifying how the event detection takes place to regulatory compliance and fulfilling requirements for different stakeholders. RAS solutions may pose economic challenges in cases where there is a requirement for generation shedding and runback, and RAS has to select minimal generation to shed based on different generation assets available. For example, it may be more economical to shed wind farms compared to coal-based generation assets. Some of the engineering challenges can include having RAS system be adaptive to different system conditions. If the information for breaker statuses are not available, there may be a requirement for detecting transmission line out of service based on analog values or metering. Identifying correct arming conditions and corrective actions may require significant studies effort. RAS have to act fast, sometimes at sub-cycle speeds, to be effective. Designing and implementing communication infrastructure for such purpose can be difficult. RAS systems can be designed to be more adaptive by considering different system states, which could be a combination of assets out of service at any given time. The actions can be different based on what system state the RAS is currently in. Similarly, the power flow or weather conditions can be used as an input to arm and select the level of remediation that needs to take place. The parameters can be selected and updated automatically for a certain time duration. If you talk about overall process of how the RAS schemes get designed and implemented, they normally start with studies to learn about system limitations, then identifying possible solutions, and then optimizing them, then selecting the best hardware and software that is required to implement RAS in the field, and then performing tests such as hardware in the loop to verify the design system is fulfilling the functionality and the initial requirements. The final step is to install and test the system in the field. With this, I would like to hand the microphone over to Mr. Ashish Upreti to present details on RAS detection and action methods.
Thank you, Ramesh. Now that we have identified our objective of preventing system-wide outages utilizing wide area control to achieve power system stability, let's talk about power system stability. IEEE Task Force defines power system stability as the ability of the power system for a given initial operating condition to regain a state of operating equilibrium after being subjected to a physical disturbance. So with most system variables bounded, so the practically entire system remains intact. So what does that mean? That means system integrity is preserved when the entire power system remains intact with no trippings of generators or loads or other electrical assets, except for those disconnected by isolation of the faulted elements or intentionally tripped to preserve the continuity of system operation. When we talk about power system stability, there are three main areas: rotor angle stability, frequency stability, and voltage stability. They can be further identified as short-term and long-term. Depending on the type of disturbance, they can be also categorized as small signal and transient stability. This classification is based on the nature of instability, size of the disturbance considered, devices, process, and time span involved. Rotor angle stability is the ability of the synchronous machine within a given interconnected power system to remain in synchronism after being subjected to a disturbance. Rotor angle stability occurs due to the angular swing of some generators, leading to their loss of synchronism with other generators. During system disturbance, there may be a scenario where instability may occur due to a runaway situation, increasing angular swings, or undamped oscillation, eventually leading to system outage and equipment damage if not mitigated. Transient stability is the term traditionally used to denote large disturbance angular stability. When power system, is subjected to a severe transient disturbance, it may result in loss of synchronism among the power system asset. It is influenced by nonlinear power angle relationship that depends on the initial operating condition, severity of the disturbance, and the strength of post-fault transmission network. Some of these disturbances include faults on transmission lines, such as single line to ground, phase-to-phase to ground, and three-phase fault. Under steady-state condition, there is an equilibrium between electromagnetic and mechanical torques. When a fault is subjected to a power system, the mechanical torque stays the same. However, the electrical torque may vary. This figure shows the power angle curves for different fault types in a power system with two parallel lines. We can see how different fault types can affect power transfer capability. As anyone familiar with equal area criterion, and don't worry if you're not, we'll talk about it next slide, can agree that as much as we can minimize the impact of the equilibrium of the electromagnetic and mechanical torques, greater the chance of system survival and returning to a stable condition. If we don't mitigate the fault within the fault clearing time or critical clearing time, then we are past the point of no return. However, even after the fault is cleared within the critical clearing time, there may be an additional requirement to take further action to keep the system stability intact. Let's talk about equal area criterion, and I don't want to dive too much into calculus, considering in regards for transient stability in a two-machine power system. The power angle curve shown corresponds to the four states of the power system: the pre-fault, fault, fault with one breaker open, and post-fault. In our analysis, we will consider the left side of the machine to be an equivalent generator and the right side of the machine to be equivalent motor. In the pre-fault state, the mechanical power into the generator, the mechanical output from the motor, and the electric power transfer are all equal if we consider this as the ideal lossless system. Upon inception of the fault, the power angle curve moves from the pre-fault curve to the fault curve. The fault reduces system power transfer capability from point 0 to point 1. The mechanical power has not changed, so the generator accelerates and the motor deaccelerates, both increasing the angle delta using the trajectory from point 1 to point 2. Breaker tripping at point 3 changes the power angle curve to fault one breaker open curve. The resulting increase in the power transfer capability using trajectory from point 2 to point 3 is not sufficient, and the angle delta continues to increase using the trajectory from point 3 to point 4. Remote breaker tripping at point 4 will clear the fault. The power angle curve now moves to the post-fault state. The power transfer capability is now greater than the mechanical power, moving the trajectory from point 4 to point 5. So now the generator deaccelerates and the motor accelerates. However, the angle delta continues to increase using the trajectory from 5 to 6 because rotor speeds do not change instantly. Area 1 in the figure represents the kinetic energy added to the rotor. Area 2 represents the kinetic energy returned back to the system. Angle delta will continue to go up to that value for which area 2 equals area 1. At this point, the swing reverses, delta oscillates around the final value, and this final value is the value corresponding to the intersection of the mechanical power, which is the horizontal strut line, and the post-fault power angle curve. The oscillation is damped by the resistance in the power system, the generator voltage regulator action, then the generator governor action. If the area 2 is less than area 1, the system cannot maintain synchronism and it will go out of step. To preserve system stability, it is important to keep the accelerating area shown as area 1 as low as possible. Fast fault clearing reduces this area and enhances system stability, and further RAS action can prevent system-wide outage. Another form of stability that we can take a look at is frequency stability. Frequency stability is the ability of the system to maintain steady-state frequency within a nominal range following a disturbance that may result in significant imbalance between load and generation. This instability may result in the form of sustained frequency swings, leading to tripping of generator units or loads. In a small island system, frequency stability may be of a concern for any disturbance causing significant loss of load or generation. In large interconnected system, frequency stability could be of a concern only following a severe system upset resulting in systems splitting into one or multiple islands. Frequency stability depends on the ability of the system to restore balance between generation and load with minimal impact. Generally, frequency stability problems are associated with inadequate equipment response, poor coordination of control and protection systems. Voltage stability is the ability of the power system to maintain steady voltage at all the buses in the system after being subjected to a disturbance from any given operating initial condition. A system may operate or experience voltage instability during a disturbance, such as increase in load demand or change in system condition, causing a progressive or uncontrollable fall or rise of voltage in some buses. Due to the increased penetration of distributed energy resources, there has been a renewed interest in studying this phenomenon for various system events and responding accordingly. A system study can show the area of strength, room for improvement, and understanding of the power system behavior to provide an optimal RAS solution if necessary. Now that we have agreed high-speed fault clearing and subsequent RAS action is necessary in severe power system disturbance to maintain system stability, and prevent wide area outage, let's focus on the challenges that Mr. Ramesh Syed talked about during our introduction section. The most pressing question in any of our schemes are when to act and what actions to take. For RAS to be successful, an in-depth understanding of power system behavior and a detailed analysis has to be performed. And this has to be done to identify a correct course of action that are well coordinated and in compliance with all the stakeholders. Once the issue is identified, we need to establish a detection method to detect the condition reliably every time. Let's take a look at different detection methods that are most commonly applied in today's remedial action schemes. There can be a contingency-based scheme that employs high-speed breaker monitoring. We can utilize frequency-based schemes using protective relays, or voltage-based scheme using voltage measurement from protective relays. We can utilize synchrophasor-based measurement from PMU units to detect large angle deflections, or we can also use overload-based schemes monitoring transmission corridor and thermal limitations. There can further be fault-based schemes that examine severe faults in the relay. But simply choosing a correct detection method is not sufficient in most cases to mitigate power system disturbance. There can be need for different types of schemes, both slow speed and high speed, open and closed loop. For example, a load generation imbalance, it's imperative to react quickly so that extreme frequency excursion resulting in frequency instability and system outage can be avoided. However, a supplementary close control is necessary to manage system conditions within operational boundary as voltage regulation to prevent voltage instability in a power system. SEL Powermax Utilities solution utilizes both of these controls using a singular controller due to its inherent nature of multi-thread processing. Subsequently, there could be a situation where we are trying to protect the system from thermal or electrical overload. And this could be a slow detection method, and the response to mitigate this can also be slow. Furthermore, there may be a requirement to manage the power flow through some transmission corridor so that system stability is not in jeopardy. And these type of controls can also be slow and closed loop so that we can minimize the impact. Now that we've looked at both slow speed and high speed controls requirements, let's dig a little bit deeper on what we do utilizing fast acting load generation balancing control system. These type of RAS systems are very common in today's world. They include contingency-based load shedding system, contingency-based generator shedding and runback, centralized frequency-based load generation balancing scheme, which can be further enhanced by using rate of change of frequency. Some of the contingency may be detected using synchrophasor-based techniques, where breaker status may not be reliable or too many to consider. As Mr. Ramesh mentioned, these systems may track system state and can be adapted to adjust their actions depending on system event. For example, if load shedding is required for a given contingency, however, if a RAS system sets a load that is already offline, it won't do us any good. Another area that should be considered to preserve system stability during power system disturbance is voltage requirement. Remedial action schemes can be implemented to avoid voltage collapse by not just load generation balancing, but controlling shunt reactor banks, shunt capacitor banks, controlling series compensation, HVDC runback, static bar compensator control. All of these control systems needs to be well coordinated. For example, voltage regulation, we may decide to take an action to turn on line reactors after performing load generation rebalancing. But there can be a localized control to control that reactor bank, or on-load tap changers, or static bar compensator or other bar compensating equipment. There is an inherent need for centralized and localized control and a coordination in between for a successful system operation. Another area of objective that a RAS scheme can help to meet is to be able to maximize transmission capability. This could be due to emerging loads or change in electrical infrastructure, or simply maximizing the usability of current asset while protecting against overload. This not only helps in providing resiliency, but also maximize our rate of return on our electrical infrastructure, or they can be supporting new load centers while electrical infrastructure is under development. It can also allow operators to monitor power flow such that system operators can operate the system within a stable operating boundary by managing risk to provide safe, reliable, and economical supply of power. Our electric power system industry is evolving. Today, we have more wind turbines and photovoltaics that are being integrated into the bulk power system. There are major benefits of utilizing these distributed energy resources as they provide green and renewable source of energy. However, the dynamic nature of these energy sources, where sun can be shining and the wind can be blowing 1 minute and gone the next, can reduce the overall inertia of the power system. These dynamic sources are continually being added to the power grid, adding opportunities to create more resilient operation of power system. The inverter-based distributed energy resources, such as PVs and wind turbines, and energy storage system have a much different characteristics in comparison to traditional sources of generation. While they may lack the short-term capability of a rotating generators, they can, in some instances, such as inverter-based energy storage system, can offer 4-quadrant control. SEL Powermax Utilities Remedial Action Scheme Solutions identifies those opportunities and integrates them as part of the control scheme, so they can be integrated seamlessly with the bulk power system, making it more resilient, safe, and economical. Our microgrid control system expert, SEL Principal Engineer Mr. Will Allen, detailed on how we can integrate these microgrids and these distributed energy resources into a larger control system to provide grid services during third session of our Powermax webinar series. Now that we've looked at wide area control, let's take a little bit deeper into wide area monitoring. A typical SCADA measurement might not be able to provide an accurate representation of a power system event. Most power system operators rely on SCADA data as primary measurement or method for communicating power system data for visualization, analysis, and operational decision. SCADA data are usually scanned asynchronously and updated once every second or so. By utilizing synchrophasor-based monitoring system, we are able to take a look at this data at a much higher resolution, painting a better picture of the power system event. This will allow operators to make a more informed decision, provide better situational awareness, and even better, automating some of these control decisions. One thing to consider while designing a RAS system includes arming criteria. Any RAS system requires a system analysis and system studies that can be performed to identify this arming criteria. This arming criteria may include thresholds, such as power flow above a certain threshold, monitoring of a system state, tracking of a system topology, so that RAS scheme may be able to provide a dynamic but informed decision. Once the contingency is detected, there may be a requirement to define a mitigating action based on system conditions, type of contingency, and its effect on system stability. The load generation rebalancing, HVDC runback, and other control could be prioritized based on the needs and requirements. There may be a need for certain critical feeders to continue to operate without interruption, and that can be managed. Here we can see a typical communication architecture for a wide area remedial action scheme. There are centralized controllers, historians, engineering workstations, operator HMI, synchrophaser-based monitoring screen within a typical communication network for a remedial action scheme. These type of systems include a time domain-based communication infrastructure with network redundancy in mind. At the substation level, there are local relays that act as contingency detection and mitigation devices that communicate to the local front-end processor, which in turn communicate this data to a centralized controller to make a more informed decision. This way, the RAS is designed in a modular and scalable approach. In case of a localized RAS, these local protective devices or detection and mitigation devices can also act as controllers. In some cases, there may be a need for both local decentralized and centralized RAS for a given power system, and these relay-based local RAS may operate in case of unavailability of a centralized RAS, adding to system resiliency. NERC PRC 12-2 identifies that a RAS system should not have a single point of failure, and we should have options for redundancy such as dual redundancy or triple modular redundancy. SEL Powermax Utilities RAS system offers different options when it comes to redundancy. We can have a dual primary system where both systems are always active. We can offer a triple modular redundant system where 2 out of 3 voting scheme is required for any RAS action. And in some cases where we need ultra reliability, there may be a need for dual TMR, which is available as part of SEL offering. While designing ultra reliable RAS, you may not want to rely on just hot standby for high-speed action. So we offer dual primary with sub-cycle response time. Our remedial action scheme expert, Mr. Bharat Naik, will talk about these solutions in a little more detail in the following sections. Now that we've looked at the basics of a typical RAS system and control action, let's dig a little bit deeper on what can we do better. How can we innovate? Currently, we offer active power-based load shedding where we can enhance our control scheme by utilizing reactive power as well, so that we can offer a reactive power-based load generation balancing. We looked at high-speed load generation rebalancing to keep the frequency inside the regulation limit, but these actions may not account for voltage or reactive power imbalance as they focus primarily on power and frequency. Frequency is a global phenomenon, but voltage is local, so we can utilize distributed voltage and reactive power measurement and offer reactive power-based load generation rebalancing. These type of control will take action based on reactive power discrepancy to support voltage profile such that overall system voltage will remain within operational limits. Our principal engineer, Dr. Abdul Rahman Khatib, talked about this concept in detail during our first session of Powermax series. If you didn't get a chance to watch it, the webinar series is available as a recording on our website. Furthermore, we can take a look at real-time data and use real-time analytics to intelligently monitor these time series data to monitor power system condition and provide situational awareness to the operators in real time. The high-resolution data may be able to capture things that may be missed by typical SCADA type measurement. Furthermore, we can utilize this new time series information and take action in real time as electric power moves at the speed of light, and even the fastest human being or superhero Flash may not be fast enough. We have need for speed. Another thing we can consider rather than relying on traditional frequency-based load generation balancing, which has been prevalent in North American market since late 1960s, is by utilizing the rate of change of frequency along with deviation in frequency. This will allow us to make a more informed decision on the amount of load or generation to shed. As more and more distributed energy resources are being integrated into the bulk power system, it may be imperative to speed up some of our controls, along with coordinating them to mitigate any cascading system-wide events. As we all may know already, misery loves company, so usually when there is a power system event, additional events may follow. RAS systems currently typically only look at single event. However, we can look into simultaneous and back-to-back events. These type of RAS schemes can offer multiple back-to-back events and on multiple locations controlled by a centralized controller or a coordinated controller. We can address multiple events using singular control platform so that coordinated control is achieved. Utilizing continuous monitoring during transition, we can track the imbalance so that an informed decision can be made in real time with minimal impact. And this can be adjusted based on system configuration after earlier events. Let's take a look at a few examples. The Jim Bridger Power Plant, located near Rock Springs, Wyoming, is a mine-mouth coal-fired generating station. This is jointly owned by PacifiCorp and Idaho Power Company. Jim Bridger operates 4 530-megawatt units that transmit majority of their power through 345 kV transmission lines to southern Idaho and 230 kV lines connected to Wyoming. Wyoming, with its abundant wind generation capability, has seen significant growth of wind farms in its eastern region. Some of the wind farms are being connected to the Jim Bridger Power Plant, and the power transmitted to the west of Jim Bridger now includes power produced from these wind farms. This sub-cycle remedial action scheme includes integration of these wind farm units as well as a part of this algorithm to preserve system stability while allowing system operators to push more power through their existing transmission infrastructure. Meanwhile, protecting against several known dynamic stability issues such as out-of-step tripping. This is a dual triple modular redundant remedial action scheme utilizing proven substation grade IEC 61131 compatible programmable controllers, protection grade relays, and high-speed IOs. Each RAS system consists of 3 identical controllers gathering IOs, performing 2 out of 3 voting on the data, and performing calculations to decide if an action is necessary. The total round-trip time from input assertion to output contact is in milliseconds or at sub-cycle speed. An action, for example, generator trip or capacitor insert bypass, cannot be executed unless 2 of the 3 systems agree in a triple modular redundant RAS. Let's take a look at this in a simplified example. When there is a fault on line 2, the impedance between generation and load increases, causing an increase in the power angle. If a corrective action is not taken swiftly, loss of synchronism or out-of-step tripping may occur at the generation facility. There can be a scenario where the remaining line may also trip due to an overload. A RAS may be programmed to trip the generator. It can be selected based on priority and operating condition for a line loss contingency that will result in minimized impact on power delivery. The result, lights stay on and customers are happy. Let's take a look at another example, this time for a countrywide scheme. Georgia State Electric System has implemented a centralized and distributed remedial action scheme to maintain power system stability in the Republic of Georgia. The countrywide remedial action scheme was based on customized operating principles devised especially for GSE's power system. The system started out as a simple 2 substation system to a mess of now more than 30 distributed controllers. The figure here shows a high-level picture of GSE's power system. The main generation source is Ingouri Hydroelectric Power Plant located in the western side of the country. The Ingouri Hydropower Plant represents about 30% of total installed capacity of GSE's power system. For the system as a whole, almost 80% of generation is hydro. During summer months, high level of water flow makes hydroelectric power more efficient than thermal generation. Georgia's main load is located in the east of metropolitan city of Tbilisi. The 500 kV transmission system is the backbone of the power system, and the sub-transmission level is at 220 kV. GSE's power system has international connections to Russia, Turkey, Azerbaijan, and Armenia. Importing power can be particularly important during winter months. During summer, which is characterized by large water flows, a surplus of generated energy can be exported. Georgia's blackout-brownout history has shown that power system can become unstable in case of any major contingency event, such as loss of a major transmission line. Angular stability can relate in catastrophic events experienced by power system in previous years. GSE implemented a RAS solution starting with decentralized and finally moving to a centralized approach. Currently, both centralized and decentralized RAS are active. Decentralized RAS will only take action if centralized RAS is not available. This project represents the evolution of the RAS logic and describes the stability criteria and the power system studies that were performed to specify these requirements. It also describes the controller logic for identifying contingency and explains the unique arming logic providing security during power system operation. These arming logic and control schemes has prevented many unintentional operation of the RAS on several occasions. Let's see an example of what happens in the case of a line outage. The power flows along the 500 kV transmission network from Inguri Dam to Tbilisi. High demand puts additional stress on the transmission network. When a line between Justaponi and Tbilisi trips due to a fault, the underlying 220 kV network gets overloaded and they trip, causing system separation and eventually a system-wide area outage. Now let's analyze this scenario and see how we can help. We experienced a permanent fault on a 500 kV transmission network. We lost that transmission line, causing our sub-transmission 220 kV network to overload, or our generators could go out of step. We can come in and we can say, as soon as we detect the loss of 500 kV transmission line, we can trip the generation near Inguri Dam. We can trip loads at the Tbilisi region. If we were exporting power, we can run back the HVDC link to reduce system loading. We can control reactor banks to keep the voltage within regulation. And with all these course of action, the result is system outage is prevented and we have happy customers. So far, we have discussed the RAS objectives and challenges. We've looked into different forms of power system stability and how RAS can help us achieve for those power system events. We also looked at what we can do better or what we can innovate from what we currently have. Now our RAS expert, Mr. Bharat Nayak, will discuss system testing and PRC 12-2 testing requirements.
Thank you, Ashish. Now that we've discussed the objectives and strategies of a RAS control system, we will focus on the system testing and validation. RAS systems are wide area schemes that are put in place to operate for an extreme system condition. Failure to operate may jeopardize system stability, and one outage could cascade into several outages. Therefore, ensuring the effectiveness of the RAS is critical. Another consideration that must be given importance to is the RAS action. Studying the impact of the RAS action is also important and vital to the RAS solution. The goal here is to ensure that post-RAS action, there is no system violations. This step allows to improve RAS actions in case supplementary actions are required. Deterministic operation of the RAS is essential to the stability of the systems. Hence, meeting round-trip time requirements is critical. Latent failures are failures that happen over time. Such failures will also inhibit the RAS operation. Therefore, regular testing and maintenance is critical. A multi-layered approach is implemented during the development and testing phase of RAS schemes. Testing methods like automated batch testing, negative testing, scenario testing, etc. are performed to ensure every component of the RAS scheme is tested. This slide talks more about the process that goes into building an EMTP model for hardware-in-the-loop testing. A phase-gated approach is implemented. Data acquisition phase is the first phase wherein the power system model of the appropriate network is built. For example, the 2022 transmission network representing a heavy summer load. The second phase is the analysis phase. In this phase, analysis is performed depending on the objective of the study. In some cases, load flow analysis or short circuit analysis is performed. And in other cases, TPL 001-4 contingency analysis, that is steady state and transient stability study, are performed using automated scripts. The outcome of these phases are then funneled in to the model validation phase. Validation is the key step in model development phase. In general, there are two schools of thoughts. One, if field data is available, then perform validation, field versus simulation. The other school of thought is validate amongst simulation softwares. In this case, an RTDS response is validated against the PSSE response. Both the validation methods help build a test bed that is apt for simulating the severity of the system. At SEL, we perform controller hardware in the loop testing during factory acceptance testing. This not only allows us to deliver a control system of highest quality, but also acts as an insurance plan to avoid any potential modifications in terms of requirements, cost, and schedule impacts. Diving into the details of controller hardware in the loop. Once the test bed is created, the RAS control system in its entirety, including detection device, action devices, I/O modules, controllers, HMI, are all connected in closed loop with the RTDS model. This setup allows us to simulate operational contingencies such as N-1s, N-2s, or closely timed contingencies, and study how the RAS will help when subjected to these outages. This setup also helps us to run free-form cases. If any abnormalities are found, they are addressed before taking any further steps. Here is a quick summary of the HIL advantages. Gain years of equivalent experience. Discover oversights before they are operational. Playback an outage and assess the effectiveness of the RAS system. By far, this has been one of the most important features of HIL. Funnel in sequence of events from an actual operation and run it through controller hardware in the loop. And at last, innovate or explore design changes. NERC PRC 12-2 is a compliance requirement for RAS systems. It provides us guidance on different design aspects of the RAS system. In the coming slides, I'm going to talk more about requirement 8 that deals with periodic testing and maintenance. NERC PRC 12-2 requirement 8 talks about functional testing and segmented testing of the RAS at site. Functional testing refers to the testing method where the actual functionality of the RAS is to be tested, meaning the input states that drive detection to action needs to be tested. I do want to remind the audience that these tests are not lab tests, but are site tests that are performed to identify latent failures. The setup demonstrates a NERC PRC 12-2 compliant online simulator. The setup shows a dual TMR scheme where RAS A can be put into test mode and RAS B is live and protecting the system. In the simulator mode, both functional testing and segmented testing is allowed using playback mode and operator mode. A playback mode is a test mode via which a sequence of events is played back into the RAS to assess RAS actions. An operator mode is a mode where the operator can dispatch set points, run a load flow, and then perform outages. Under both the modes, a test report is generated to illustrate the RAS actions. NERC PRC 05-6 talks about implementing programs for maintenance of all devices that may affect reliability of bulk electric system so that devices are kept in working order. Using the SEL's RTAG, you can build an automated system that will verify commissioned IED settings, firmware configuration, generate automated reports for both local and remote access, assess the health of breakers and trip coil assemblies, verify CTs and PTs with continuous IED measurements, verify the communication assisted protection channel integrity, monitor IED diagnostics, and so forth. This slide shows the automated test report. The event report here provides the operator a report that gathers all pertinent information about the event. Information such as what's the RAS event name, amount required to shed, amount selected to shed, timestamp, which RAS controller acted. A wide area scheme needs a wide area coordination of systems and stakeholders. Coordination between the dispatch centers and load or generation centers are critical. This slide shows the flow from detection to action, from start to finish. A line loss outage is detected and reported to both RAS A and RAS B controllers. The RAS controllers exchange information to ensure quality and then send trip commands to the appropriate generation or load centers, start to finish within sub-cycle times. With this slide, I would like to summarize all the key design questions that help in designing a RAS system. What is your RAS designed to solve? Is it thermal overload issue or a voltage collapse issue? How is redundancy being designed? Is it a RAS that is limited impact or other RAS? Is single point of failure allowed? How reliable is your communication network for a RAS solution? Is your RAS scalable for future expansions? Does your RAS system provide intuitive diagnostics such as automated test reports? How do you measure effectiveness of the RAS design before installation? Is HIL required? Does online simulators improve testing and maintenance? With that, I conclude the presentation and hand it over to Tristan. Thank you.
Thank you, everyone. Now we've arrived at the Q&A portion of our event. As a reminder, please submit your questions to all panelists with the Q&A tool at the bottom right-hand corner of the application. For our first question, is Powermax for utilities capable of detecting simultaneous contingencies?
Absolutely. The Powermax utilities is capable of detecting simultaneous contingencies. The contingencies can be defined as single event contingencies or N-1, such as loss of single transmission line. The contingencies can also be defined as double event N-2, such as loss of two transmission line, and so on. So yes, the simultaneous detection is possible.
Thank you very much. We have another question. Which communication protocols can be used with Powermax for utilities?
I can take that, Tristan. This is Ashish. SEL Powermax Utilities RAS can employ most of the industry standard protocols. The communication protocols are selected based on application, as we discussed in our slides, high speed or low speed, analog or digital. The high speed monitoring and control protocols such as IEC 6150 GOOS, 6150 MMS, DNP, or Modbus can be utilized. If there's any specific project need, we can talk about that as well in greater detail.
Thank you, Ashish. We have another question here. How do you identify if a RAS is a limited impact RAS or another type?
Thank you, Tristan. This is Bharat. I'm going to take this question. The answer is studying the problem statement using a simulation software will help in understanding the impact of contingencies on the system. PRC 12-2 and TPL 001-4 provides guidance on identifying whether it's a limited impact RAS or other RAS. In general, for each contingency, stability criteria are evaluated, and based on the outcome, the RAS identification is derived.
Thank you, Bharat. We have another question from one of our viewers. How do you know when HIL testing is needed?
Hi, Tristan. I can take this one. A long time ago when I was in school, a professor of mine, he used to say, all control systems are same but different. Same concept still applies today, right? All RAS are similar but different. Having a hardware-in-loop testing allows us to test these algorithms using the highest fidelity available. And as things have progressed, hardware-in-loop testing process has greatly improved. They are much more easier to implement, very affordable, and have significantly reduced, the added value of doing it. They add a lot of value by doing them. We can utilize hardware-in-loop testing not just to test the algorithm, but also to mitigate the risk and learning to validate the design prior to getting out in the field. Because trying to change things or fix things in the field is going to be very troublesome. It will also allow us to test the scenarios that we may never be able to test in the field, right? We may not be, apply real, faults or such behaviors. That can all be done in the lab, in the in-house, with the controller in loop, providing us with the highest fidelity. So in short, yes, we definitely recommend it, highly recommend it. Now, depending upon RAS type, we do have some other forms of testing method that we can offer from SEL. We actually have in-house patented universal power flow algorithm. If the RAS doesn't have any transient issues, we can utilize that to test. If there's any particular projects that the presenter or that the audience had in mind, they can reach out to us and we can have more elaborate discussion.
Thank you very much. All right, another question. With the RTAX mirrored bits protocol, it only supports digital signals. Is there a plan to support analog in the future?
Hi, Tristan. I can take that. It's Ramesh. As of now, mirror bits are not going to able to support analogs, but there are some methods that you can use to send analog quantities through mirror bits. However, what we recommend nowadays is to use Ethernet-based high-speed protocols such as IEC 6750 Goose that has both digital signals and analog signals capability to transfer that data over high speeds.
Thank you, Ramesh. Okay, we have another question. Is Powermax able to use synchrophaser data for disturbance detection? And is the HIL testing able to simulate synchrophaser data?
Yeah, that's a great question. In fact, for one of the RAS schemes that we looked at, Georgia State Electrosystem, we did implement a synchrophaser-based monitoring. And using a synchrophaser vector processor, we analyzed their data for quite some time to see if there's any necessary action that we need to take utilizing that data. There was another remedial action scheme that we implemented for our country of Peru, where it was all based on synchrophaser data. We're looking at positive sequence voltage angle across multiple substations, and based on that, we're doing a detection of a line was being lost or any power system event, and take action based on that. So yes, there are actually some systems that are in place that utilizes synchrophaser-based data as well.
Excellent, thank you. And I think we have time for one last question. Someone asked, how do you secure the communications infrastructure?
Yeah, I can take that, Tristan, as Ramesh. So security is depending on, sometimes the facility, it may be required that that facility is NERC compliant. So in terms of security, we have to look at, user authentication levels, communication protocols, and if it is a NERC compliant system that is required, you have other things that you have to kind of consider, as well as, we have to look at patching methodology, if there's any Windows-based components, as well as firmware upgrades and future upgrades of the system. Overall, what we try to do is make sure there are appropriate firewalls that are in place, and we have SEL has integrated defense group that can help in going in greater details in identifying what current resources you have, what kind of mitigations that you need for cybersecurity side of things, and then from the design level, we will go through these processes to make sure everything is documented and is in compliance.
Thank you. All right, now we have reached the end of the webinar. If your question was not answered live or via the Q&A tool, you'll receive an answer from our experts via email. If you'd like to learn more about this topic, you can also visit our website. We hope everyone enjoys today's event, and we look forward to seeing you all in future SEL webinars. Have a great day.